everyone, welcome to video 3 of 3 on partial fraction decomposition for Math 1452 at Texas Tech University, which is Calculus 2. So in the first video, we talked about partial fraction decomposition and what that meant and how to set it up. In the last video, we looked at examples of using partial fraction decomposition when that denominator had linear terms only. And now in this final video, we will look at how to use partial fraction decomposition when we have quadratic terms. So again, we need to solve for some coefficients, but what we're going to do is we're going to expand our equations and include coefficients. So to start off, let's just rewrite the setup that we had from that very first video. So our initial setup was rewriting the fractions in our integrand. That over just a bit. Over x times x squared plus 1. So remember that we broke this into a fraction with an x on bottom and an a on top, and an x squared plus 1 on bottom. And remember that if our denominator is quadratic, then our numerator has to be linear. Okay? So to solve for a, b, and c here, what we're going to do is the exact same thing as before. We multiply both sides of the equation by our initial denominator. And just like before, on my left-hand side, that entire denominator is going to cancel. So I'm just going to be left with an x squared minus 1. And then when I distribute on my right-hand side, my x is going to cancel in my first term, so I'm just going to be left with a times x squared plus 1. And my x squared plus 1 is going to cancel for that next term, so I'm just going to be left with bx plus c times x. So what we're going to do now is we're actually not going to plug in strategic values of x. And the reason for that is that there's no value of x that's going to make that x squared plus 1 equal to 0. So with our quadratic terms, they are not factorable. That's why they are quadratic terms here. So because they're not factorable, that means there's no value of x that's going to make them be 0. So we need to try a different strategy. And so what we're going to do is we are going to just FOIL out our right-hand side. So when I do that, I get ax squared plus a plus bx squared plus cx. And I am going to combine my like terms. So my coefficient of x squared is a plus b. My coefficient of x, c. And my constant is. So what I mean by equating coefficients, I'm going to look at the different powers on x on both sides of my equation. So I can see that. I'm going to do some underlining here. I have 1x squared on my left-hand side of my equation, and I have a plus bx squared on my right-hand side of it. So that gives me a new equation where my 1x squared has to be equal to a plus bx squared on my right-hand side. Next, I can look at my coefficient. So I don't have any x terms on my left-hand side, so that means the coefficient is 0. And on my right-hand side, I have c as my coefficient of x, so that tells me that c equals 0. And lastly, I am going to look at my constant term, and my constant term on my left-hand side is -1, and my constant term on my right-hand side is a. So I'm going to have -1 equals. So from these three equations, we can see that we've solved for c and a already. So now we need to solve for b, and we can do that by combining these two equations so that I have 1 equals a plus b. Well, I know that a is equal to -1. So when I add 1 to both sides of this equation, I get that 2 equals b. So we can combine those first two equations to give me an equation that solves for b. So now I just rewrite my fraction like I did for my linear terms. So I have x squared minus 1 over x times x squared plus 1 is going to equal -1 over x plus my b is 2 and my c is 0, so that numerator is c. Sorry. So again, remember that our motivation is to integrate. So now this has turned into two things. So remember, I'm not going to verbal write out what these integrals are, but we can see that that -1 over x is going to use an anti-differentiation rule to integrate to be the natural log of x, negative in front, and then that 2x over x squared plus 1 is solved using u substitution, where our u is our denominator. And then we can proceed just using the strategies we learned in Calculus 1. So next I'm going to go ahead and go over to example 4. So in example 4, first off, I'm going to start by, again, just rewriting our setup from the first video. So remember that because this is quadratic, one of our terms is x squared plus 2, and when we have a quadratic in our denominator, our numerator is linear. And then because it's repeated, we need a second option when that denominator is squared, and then because it's quadratic, we have a. So again, our first step is the exact same. We're going to multiply both sides by our initial denominator. And as usual, our left-hand side, that denominator is going to completely cancel. And on our right-hand side, we're going to distribute. So we get the equation 8x cubed plus 13x equals. And for ax plus b, one of the x squared plus 2 terms is going to cancel, but one is still going to be there. And for the cx plus d term, because we had 2 in the denominator and we're multiplying by another 2, those are going to. So just like in example 3, what we're going to do is we're just going to expand our right-hand side. So that means we're going to FOIL here, first, outside, inside, last, and then we're going to combine our like terms. So our first gives us ax cubed, our outside gives us 2ax, our inside gives us bx squared, and our last gives us 2b. And then we're going to add cx and d. So we're going to combine our like terms. So that means that we look at our powers of x. So there's only one term with x cubed, and that has coefficient a. There's only one term with x squared, and it has coefficient b. There are two terms with an x, and they are 2a and c, so we just add those together. So we have 2a plus c times x, and then we just add our constant terms together, which is 2b plus. So again, what we're going to do are we're going to equate coefficients. So we look at our cube term, and we can see that there's 8x cubed on our left-hand side and ax cubed on our right-hand side. So that's going to give us the equation 8. Next, we look at our squares. So there are no square terms on our left-hand side. So that tells us that 0 equals our coefficient of x squared on our right-hand side, which is 2. Next, we look at our coefficient of x. So there are 13 x's on our left-hand side and 2a plus c x's on our right-hand side. I'm going to go ahead and underline those. And last, we look at our constant terms. So there's no constants on our left-hand side and 2b plus c on our right-hand side. So we have 4 equations that we're solving. And so the first 2 already tell us what a and b are. So we can just use those and plug in a to our third equation and plug in b to our fourth equation to tell us how to solve those. So plugging in a equals 8 makes our third equation 13 equals 16 plus c. And subtracting 3 from both sides is going to tell us that -3 equals c. Next, plugging in b equals 0, our last equation, is going to just tell us that 0 equals c. So again, I'm just going to box where we solve for a, b, c, and d, just so it's a little bit more clear. And now that we've solved for our variables, we are going to rewrite our fraction. So we started with 8x cubed plus 13x over x squared plus 2 squared. And our ax plus b is just going to be 8x over x squared plus 2. And our cx plus d is just going to be negative 3x over x squared plus 2 squared. So again, remembering that our motivation is integrating these things. Now, our term 8x over x squared plus 2 can be solved using u substitution, where u is that denominator. And our term negative 3x over x squared plus 2 squared can also be solved using u substitution, where u is again that x squared plus 2. And we're going to integrate that using the reverse power rule. So feel free to work out the rest of these examples on your own, but like I have mentioned in the previous video, I'm not going to be explicitly writing that out here. But this is all for the video series on partial fraction decomposition. We hope this helps, and good luck.